We now come to David Archibald. He's up from the land of Oz. I never understand why they don't get the blood rushing to their head down there, but he's come all the way up with a remarkable range of scientific knowledge in the cancer field, oil exploration, trials on a formulation he invented with professors from Purdue University, Indiana, currently underway at Queensland University. Knows a lot about oil. So they've got to hate him. And he's going to tell us about the next solar cycle, which, if it gives me a suntan, will please me. Thank you very much.
Do we live in a special time in which the laws of physics and nature are suspended? No, we do not. Can we expect relationships between the sun's activity and climate that we can see in data going back several hundred years to continue for at least another 20 years with absolute certainty? In this presentation, I will demonstrate that the sun drives climate and use that demonstrated relationship to predict the Earth's climate to 2030. It is a prediction that differs from most in the public domain. It is a prediction of imminent cooling. To put the solar-climate relationship in context, we will begin by looking at the recent temperature record and then go back further in time. Then we will examine the role of the sun in changing climate, and following that, the contribution from anthropogenic warming from carbon dioxide. I will show that increased atmospheric carbon dioxide is not even a little bit bad. It is wholly beneficial. The more carbon dioxide we can put into the atmosphere, the better the planet will be for humans and all other living things. The satellite record is the highest quality temperature data series in the climate record. We have 30 years of that. It shows that the temperature of the southern hemisphere has been flat, with a slight increase in the northern hemisphere. Note the El Nino peak in 1998. Globally, we've had 10 years of temperature decline since that peak in 1998, with a rate of decline of 0.06 degrees per annum. I am expecting that rate of decline to accelerate to 0.2 degrees per annum from the end of this decade. The satellite record is corroborated by the record of Antarctic and Arctic sea ice extent over the same period. There is no long-term trend evident. Most recently, there has been a 1 million square kilometre increase over the long-term mean. That is a 5% increase. Most rural temperature records in the United States were set in the 1930s and 1940s. Greenland had its highest temperatures in the 1930s and has been cooler since. That is why it is possible to select a number of rural US temperature records and come up with a reconstruction that shows that it is cooler now than it has been, was 70 years ago, and in this case, appreciably cooler than what it was 70 years ago. The 1.5 degree temperature decline from the late 1950s to the mid-1970s was due to a weak solar cycle 20 after a strong solar cycle 19. I believe that the Earth is a very sensitive thermometer to changes in the sun. That rural US data set shows a good correlation with minute changes in total solar irradiance in watts per square metre, suggesting that the Earth is indeed a very sensitive thermometer. This is total solar irradiance from the Hoyt-Shatton reconstruction with 11-year smoothing, less 1,350 watts per square metre. The peak US temperature was in 1936, at much the same time that total solar irradiance peaked. If you have wondered why US temperatures are still lower than what they were 70 years ago, the fact that total solar irradiance is lower than what it was 70 years ago might provide an explanation. We will progress on to far better solar temperature correlations. After the invention of thermometers, records started to be kept. This is one of the longest temperature series. A number of interesting things can be seen in this record, including the depths of the Little Ice Age, in the late 17th century, when the Thames regularly froze over, and the Dalton minimum, which was the last time the Thames froze over in the City of London. The warm period of the 1930s and 1940s seen in the US data set is also seen here. What is also interesting is the 2.2 degree temperature rise from 7.8 degrees in 1696 to 10 degrees in 1732. This is a 2.2 degree rise in 36 years. By comparison, the world has seen a 0.6 degree rise over the 100 years of the 20th century. That temperature rise in the early 18th century was 4 times as large and 3 times as fast as the rise in the 20th century. The significance of this is that the world can experience very rapid temperature swings, all due to natural causes. The temperature peak of 10 degrees in 1732 wasn't reached again until 1947. To reconstruct climate prior to thermometer records, isotope ratios and tree ring widths are used. This graph shows the medieval warm period and Little Ice Age. The peak of the medieval warm period was 2 degrees warmer than today, and the Little Ice Age 2 degrees colder at its worst. The total range is 4 degrees centigrade. The warming over the 20th century was 0.6 degrees by comparison. The recent warming has melted ice on some high passes in the Swiss Alps, uncovering artefacts from the medieval warm period and the prior Roman warm period. It was warmer again not long after the last ice age ended. Sea level was 2 metres higher than it is today. Since the Holocene optimum about 8,000 years ago, we have been in a long-term temperature decline of 0.25 degrees per 1,000 years. When I asked at the beginning of this presentation if we lived in a special time, well, that is true in relation to the last 3 million years. The special time we live in is called an interglacial. Normally, and that is 90% of the time, the spot I am standing on is covered by several thousand feet of ice. Relative to the last 4 interglacials, we may be somewhere near the end of the current interglacial. The end of the Holocene will be a brutal time for humanity. To paraphrase Thomas Hobbes, interglacials are short, and then we enter the nasty brutishness of the glacial periods. This graph suggests that may be soon. It shows the last 5 interglacials of the Vostok core superimposed on each other, all aligned on the peak temperature reached in each interglacial. I have expanded a portion of that on the right-hand side. The Holocene, the period we are in now, is tracking along with 3 of the previous 4 interglacials. Of those 3, if the Holocene ends up being like the Eemian, then we may have up to 3,000 years of Little Ice Age-like conditions before we plunge into the next glacial period. If not, the plunge could start any time now. The energy that stops the Earth from looking like Pluto comes from the sun, and the level of that energy does change. This graph is of sunspot cycles since 1700. The average length of a sunspot cycle is about 11 years. The Dalton minimum was a period of lower temperatures from 1796 to 1820, caused by the low amplitude of solar cycles 4 and 5. We are currently near the end of solar cycle 23. When solar cycle 23 ends is very important, as we will see in the next few graphs. This graph shows the temperature response to solar cycles of the Dalton minimum at 3 European stations. There was a 2-degree decline at Oberlach in Germany over that period. There is a better correlation between temperature and solar cycle length, rather than with solar cycle amplitude. I produced this graph using data from De Bilt in the Netherlands. The slope of the line is 0.6 degrees centigrade per year of solar cycle length. A strong relationship between solar cycle length and temperature is seen in other data sets. This is a figure from a 1996 paper by Butler and Johnson of the Amar Observatory. The slope of the line is 0.5 degree centigrade per 1 year change in solar cycle length, which amounts to 1.4 thousandths of a degree per day. Let's assume that the relationship demonstrated nearly 200 years of Amar data and 300 years of De Bilt data is valid today. I have plotted on top of the original figure solar cycle 22, which was 9.6 years long. Solar cycle 23 hasn't finished yet. The first sunspot of solar cycle 24 was seen on the 4th of January 2008, but the month of solar minimum may not be until mid-2009. I have plotted on this figure what a 13-year-long solar cycle 23 would look like. It follows that the temperature at Amar will be 1.6 degrees lower. This effect is upon us right now. In a few short years, we will have a reversal of the warming of the 20th century. If solar cycle 24 is as weak as a number of solar physicists are predicting, then solar cycle 23 may be 13 years long or longer. The solar cycle preceding the Dalton minimum was 13.6 years long. This graph shows the transition of one sunspot cycle to the next using the example of the solar cycle 22 to solar cycle 23 transition. The sun reverses magnetic polarity with each solar cycle, and sunspots of the new solar cycle start forming before the old cycle has completely died off. Solar cycle 23 started in May 1996, rising to a peak of 120.9 in April 2000. For solar cycle 23 to be of average length, solar cycle 24 should have started in January 2007. This graph is another pointer that we are heading back to the weak solar cycles of the 19th century, with 19th century type winters to accompany them. Solar cycles 10 to 15 from 1860 to 1917 had an average of 66 months from the first spotless day to solar cycle minimum. This was a time of considerable glacial advance in the European Alps. Since then, solar cycles have averaged half that at 33 months from first spotless day to solar cycle minimum. So far, solar cycle 24 is plotting on the 19th century line, with the first spotless day on 27th of January 2008. And if the 66-month observation holds, then solar minimum will be on or about July 2009. This would make solar cycle 23 13 years long. At its simplest, the relationship between solar activity and the Earth's climate is this. Lower magnetic field strength means fewer sunspots. Fewer sunspots means less solar wind. Less solar wind means more galactic cosmic rays. More galactic cosmic rays means more low-level cloud formation. More low-level clouds means that more sunlight is reflected back into space, which in turn means less heating of the Earth's surface and atmosphere. Climate is not a random walk. If you can find a solar physicist to give you a prediction of solar activity, you can use that to make a prediction of climate. We can follow the path outlined in the previous slide. Ken Shatton is the solar physicist with the best track record in predicting the strength of solar cycles, using the solar dynamo theory he co-authored in 1978. This is the basis of Ken Shatton's prediction. The red line is the strength of the polar magnetic fields in the sun, and the blue line is the strength of the toroidal magnetic fields. During a sunspot cycle, polar magnetic fields are converted to toroidal magnetic fields and then back again. Sunspots form from the toroidal magnetic fields breaking through to the sun's surface. The black line sums the polar and toroidal magnetic field strengths. This has been in downtrend since the early 1990s. This downtrend means that there is much less magnetic force available to make sunspots, so solar cycle 24 will be much weaker than solar cycle 23. Polar faculae are another sign of weaker magnetic fields on the sun. Based on the relative number of polar faculae during this minimum relative to the last, and the intervening solar cycle peak of 120, I predicted the amplitude of solar cycle 24 will be 45. This is very similar to the amplitudes of solar cycles 5 and 6 during the Dalton minimum. A weak solar magnetic field produces a weak interplanetary magnetic field. There are a few interesting features on this graph. Note the flatness of the interplanetary magnetic field associated with the 1970s cooling period during solar cycle 20. What is significant is that the strength of the interplanetary magnetic field has fallen below the levels of previous solar minima, and we are possibly still a year off the month of solar minimum. The first earthly consequence of a weak interplanetary magnetic field is a high count of galactic cosmic rays, seen here in the neutron count of the Oulu station in Finland. I have plotted on this graph what I expect to be the maximum neutron count in this solar minimum, based on what the interplanetary magnetic field strength could fall to. The increased galactic cosmic rays will cause increased cloudiness, which in turn increases the Earth's albedo, and then the world cools in search of a new equilibrium. What are the implications of all this for the United States? We will now look at some longer-term US temperature records in the context of solar cycle length. This is Hanover, New Hampshire, with a very good correlation and a slope of 0.73 degrees Celsius per year of solar cycle length of the previous cycle. This is Portland, Maine, with almost the same correlation. This is Providence, Rhode Island, with a wider spread of data points, but still a good correlation. Now let's look at Hanover again and plot up where we are currently in terms of solar cycles. Solar cycle 22 was 9.6 years long. On the basis that solar cycle 23 is 13 years long, there will be a 2.2 degrees Celsius decline in temperature in Hanover, New Hampshire, over the next decade. In terms of quantum, this is 3 times the temperature rise of the 20th century, but in the opposite direction. To date, society has only been concerned about solar cycles and sunspots and so on in terms of their effect on the longevity of low Earth orbit satellites. That is an important business, but soon the focus will change to our ability to feed ourselves. And that is a subject that will concentrate a lot of minds. The evidence from the Hanover solar cycle length to temperature relationship and that of the other cities in this presentation is incontrovertible. There will be a significant cooling very soon. Our generation has known a warm, giving sun, but the next generation will suffer a sun that is less giving and the Earth will be less fruitful. A cursory examination of the temperature map of the United States suggests that every 0.7 of a degree change in temperature will shift climatic conditions 100 kilometres. The big consequence of this is that it will shrink the growing season. The 2.2 degree decline I'm predicting will take about 2 weeks off the growing season at both ends. Next decade will not be a good time to be a Canadian wheat farmer, and being a Canadian citrus grower is completely off the agenda. Combining the rural US data set earlier and the projected temperature response to the length of solar cycle 23, this graph shows the expected decline to 2030. The temperature decline will be as steep as that of the 1970s cooling scare, but will go on for longer. It can get worse than a repeat of the Dalton minimum. Ken Shatton is the solar physicist with the best track record in predicting solar cycles. His work suggests a return to the advancing glaciers and delayed spring snowmelt of the Little Ice Age for an indeterminate period. Now, can global warming from increased atmospheric carbon dioxide save us from a collapse in mid-latitude agricultural production? Not at all. Anthropogenic warming is real, it is also minuscule. Using the Modtran facility maintained by the University of Chicago, the relationship between atmospheric carbon dioxide content and increase in average global atmospheric temperature is shown in this graph. The effect of carbon dioxide on temperature is logarithmic, and thus climate sensitivity decreases with increasing concentration. The first 20 ppm of carbon dioxide has a greater temperature effect than the following 400 ppm. Since the beginning of the Industrial Revolution, increased atmospheric carbon dioxide has increased the temperature of the atmosphere by 0.1 degrees centigrade. That isn't much. In fact, it is almost next to nothing. To the end of time, and let's call that 1,000 ppm of carbon dioxide in the atmosphere, the total effect may be good for 0.4 degrees. It is hard to get excited or concerned about such a number. It is swamped by natural variability. For example, the 2-degree temperature range of the 20th century and the 2-degree temperature fall to come over the next decade. This graph takes the data from the previous slide and summarises it in one bar. As you can see, relative to 1,000 ppm, the warming effect of carbon dioxide was over 80% saturated at the pre-industrial level of 280 ppm. Recently, Dr. Hansen of NASA made a statement that the maximum safe level of carbon dioxide in the atmosphere is 350 ppm, about 10% below its current level. To illustrate just how spectacularly idiotic that statement is, this graph shows Dr. Hansen's danger level of 350 ppm relative to the levels that the Earth has experienced from the recent to distant past. The Earth has happily survived levels more than 10 times the level that Dr. Hansen considers to be the threshold of disaster. There are a couple of things to note from this graph. One is that the carbon dioxide levels have fallen over geological time. Relative to the last 500 million years, the average natural level is around 2,500 ppm. The second thing is that prior to the Industrial Revolution, the atmospheric carbon dioxide level was bumping along at the level required to sustain life on this planet. The more we take carbon dioxide above that minimum critical level, the safer life on this planet will be. Now, this graph compares my temperature prediction of 0.4 degrees centigrade based on one of the ICCC work of 1996 on his observations based on nature, with estimates from the most prominent in this field. Commonly, sensitivity is based on what would happen if the carbon dioxide level in the atmosphere doubled from its pre-industrial level, as if this was something tragic, when we, in fact, know that it will be something wonderful when it does happen. The Stefan-Boltzmann figure of 1 degree centigrade is based on the Stefan-Boltzmann equation without the application of feedbacks. This is what would happen if there were no feedbacks involved. Bill Kinnamouth, who is with us in this room, is a former head of Australia's National Climate Centre. His estimate of the forcing is 0.6 degrees centigrade, and this is based on water vapour amplification, but also includes a strong dampening effect of surface evaporation. Richard Lindzen is a very prominent and eminent American climate scientist. His estimate of the forcing is based on water vapour and negative cloud feedback. The models the ICCC rely upon take the 1 degree of heating from the Stefan-Boltzmann equation and apply an enormous amount of compounding water vapour feedback. At their worst, the ICCC models take 1 degree of heating and turn it into 6.4 degrees. As such, these models are based on the premise that the Earth's climate is tremendously unstable, prone to thermal runaway at the slightest disturbance. The eminent climate scientists believe the opposite. This would be just an interesting divergence of opinion if it weren't for the fact that tens of millions of people stand to lose their jobs, and billions of people beyond that will suffer unnecessarily as a consequence of those modelled feedback assumptions. Before hundreds of billions of dollars are squandered, resources misallocated, and many people are driven into penury, it would be a productive exercise to examine the basis of those modelled feedback assumptions, especially when the eminent scientists in the field have the contrary opinion. Before we leave the solar and atmospheric science, it is important that other researchers are able to replicate the work I have done. It is simple enough that high school students should be able to do it. The projected increase in atmospheric carbon dioxide is likely to be brought forward if Chinese economic expansion continues for the next 10 years at the same rate it has demonstrated over the last 10 years. This graph shows emissions of carbon to the atmosphere by the United States, Australia and China, with historic data to 2005 and a projection to 2020. Chinese emissions will overtake US emissions in 2008 and then double from the current level by 2016. Per capita emissions by the three countries will be equivalent by 2020. Carbon dioxide is not even a little bit bad. It is wholly beneficial. This graph from a recent ICCC paper shows plant growth response to atmospheric carbon dioxide enrichment. The 100 ppm carbon dioxide increase since the beginning of the industrialisation has been responsible for an average increase in plant growth rate of 15% odd. The 50% increase in plant growth rate due to a 300 ppm increase in atmospheric carbon dioxide can be expected about the middle of the next century. What a wonderful time that will be. A 300 ppm increase is something that we can only dream about, but some future generation will get these sorts of benefits from the current industrious burrowing of the Chinese in their coal mines. C3 cereals include wheat and C4 cereals include maize. In a world of higher atmospheric carbon dioxide, crops will use less water per unit of carbon dioxide uptake, and thus the productivity of semi-arid lands will increase the most. It's not all good news. We will need this increase in agricultural productivity to offset the colder weather coming. It also follows that if the developed countries of the world want to be caring and sharing towards the third world, the best thing that could be done for the third world is to increase atmospheric carbon dioxide levels. It is equivalent to giving them free phosphate fertiliser. Who would want to deny the third world such a wonderful benefit? 2008 is the 10th anniversary of the recent peak of global temperature in 1998. The world has been cooling at 0.06 degrees per annum since then. My prediction is that the rate of cooling will accelerate to 0.2 degrees per annum following the month of solar minimum sometime in 2009. Dr. Hansen's idiotic statement that the maximum safe level of carbon dioxide in the atmosphere is 350 ppm begs the question of what the actual ideal level is. I have taken the 1000 ppm figure from the level that commercial greenhouse operators prefer to run their greenhouses at. The ability to grow food is going to be the overriding concern next decade. Regarding that 1000 ppm level, we will never get there. Atmospheric carbon dioxide levels have been much higher in the geological past, but most of that carbon is now bound up in the Earth's crust where we can't get to it. Half of the carbon dioxide we are producing now is being gobbled up by the oceans, in soils, and in the Russian tundra. At best, we might get to about 600 ppm. What I have shown in this presentation is that carbon dioxide is largely irrelevant to the Earth's climate. The carbon dioxide that mankind will put into the atmosphere over the next few hundred years will offset a couple of millennia of post-Holocene optimum cooling before we plunge into the next ice age. There are no deleterious consequences of a higher atmospheric carbon dioxide. Higher atmospheric carbon dioxide levels are wholly beneficial. We can be thankful to the anthropogenic global warming proponents for one thing. If it weren't for them and their voodoo science, climate science wouldn't have attracted the attention of people outside the field, and we would be sleepwalking into the rather disruptive cooling that is coming next decade.